Welcome to the next learning unit in the chapter Grid Integration. This teaching unit will deal with the influence of PV systems on the power quality. We've now become familiar with two problems that arise when connecting a PV systems to the power grid: an overload of the line due to a high current, as well as the increase of the voltage at the feed-in point. In addition, there are a number of other effects that the connection of a PV system to a power grid can bring. Let's first take a look at what factors determine the power quality in a power grid. Most power grids are operated with three-phase alternating current. Here, three alternating currents are transmitted simultaneously, which oscillate with a time offset, meaning they are out of phase. Ideally, the phase shift is exactly 120 degrees, and the RMS values of all three currents are the same, so that the three lines each carry the same power. If the different phases are loaded to different degrees, this is referred to as an unbalanced voltage. Unbalanced voltages cause the conductors to be stressed with different amounts of power. As a result, the line losses are greater than if the power were distributed evenly over the three phases. In addition, larger unbalanced loads can lead to greatly increased energy losses in the generators of power plants, which are accompanied by strong heating and can lead to destruction. In practice, certain unbalanced loads often occur. One reason for this is that most household devices are single-phase loads. A very powerful consumer can therefore result in a relatively high unbalanced voltage within a household. However, such unbalanced voltages average out in a power grid due to the large number of households. The feed-in of a PV system can also lead to an unbalanced voltage. For this reason, a three-phase feed-in is mandatory in most countries above a certain system power. In Germany, the limit value for a single-phase feed-in is 4.6 kVA. If the system power is greater, a three-phase inverter must be used. Another factor that is important for the stability of the power grid is the grid frequency. In Europe, this is optimally 50 Hz. In reality, however, the frequency fluctuates slightly around this value. This has mainly to do with the thermal power plants and an electricity grid. These largely contain synchronous generators where there is a fixed relationship between speed and grid frequency. If consumption in a power grid increases unexpectedly and suddenly exceeds the sum of the power fed into the grid, this causes the generator to slow down slightly. As a result, the grid frequency drops. The same thing also happens when the feed-in drops unexpectedly, for example, when a power plant unit fails. Vice versa, the grid frequency rises if consumption is lower than expected or the feed-in is suddenly increases. Due to the rotating masses of all generators, however, the power grid has a certain amount of inertia. In the short term, this inertia alone produces a slight stabilization of the frequency. In the case of longer-lasting frequency deviation, however, the system inertia is not sufficient to stabilize the frequency. In this case, the frequency must be corrected by active control. If the grid frequency is too low, additional feed-in is required or consumption must be reduced. If the grid frequency is too high, the feed-in must be reduced or the consumption must be increased. If the share of photovoltaic in a power grid is very large, the photovoltaic systems must also contribute to active frequency control. Since the feed-in power of a PV system depends on the irradiation and cannot be increased as required, the contribution here is usually limited to reducing the feed-in when the grid frequency is too high. In Germany, PV inverters must therefore throttle their output above a grid frequency of 50.2 Hz using a linear characteristic curve. Above a grid frequency of 51.5 Hz, the system must disconnect completely from the grid. The same applies to an under frequency below 47.5 Hz. We now come to the last power quality factor that we want to discuss today, the harmonics. First, let's take another look at an ideal AC current waveform. In the ideal case, the current oscillates with a frequency of 50 Hz and has an exactly sinusoidal curve. In reality, however, the curve usually deviates considerably from an ideal sinusoidal curve. This is where harmonics come into play. But what is an harmonic? Harmonics are waves whose frequency is an integer multiple of the fundamental. If the frequency corresponds to 3 times the fundamental frequency, it is called a third-order harmonic. In the same way, there is also harmonics of the 5th, 7th or 11th order, as well as all other integer multiples of the fundamental frequency. Note that the harmonics are shown here with lower amplitude than the fundamental. However, the harmonics can as well have equal or even higher amplitude than the fundamental. But what do harmonics have to do with alternating current? As just briefly explained, the actual shape of an alternating current usually deviates more or less from an ideal sinusoid. This is also called a distorted sine wave. With the help of the so-called Fourier analysis, every periodic signal can be decomposed into a fundamental wave and a various harmonics, also that of a distorted sine wave. Or expressed the other way around, any periodic function can be composed of a fundamental wave and various harmonics. Let's look at this with the example of a square wave. The square wave has a certain fundamental frequency. This is the frequency of our fundamental. Now add a third order harmonics with 1/3 of the amplitude of the mantle. Let's add the 5th, 7th and 9th order harmonics. The further we continue this, the closer the square wave can be approximated by Fourier analysis. The harmonic components can basically be represented as a ratio of their effective value to the effective value of the fundamental. In order to obtain a measure of the total value of the distortion, the so-called total harmonic distortion THD is commonly specified. It indicates the ratio of the effective value of all harmonics of orders 2 to 40 to the effective value of the fundamental. In addition to harmonic currents, there are also harmonic voltages. These result from the fact that the harmonic currents lead to a voltage drop at the grid impedances. Therefore, in addition to the THD of the current, the THD of the voltage is also defined. Usually the distortion of the current is given as THDI and the distortion of the voltage as THDV. An AC current with a high proportion of harmonics can have various effects. The harmonic currents do not contribute to the active power, but generate additional reactive power that oscillates back and forth in the grid. This leads to additional heating of the lines and consumers. In addition, harmonics can cause resonance phenomena in oscillating circuits consisting of coils and capacitors, which can lead to very high harmonic currents or voltages. For these reasons, there are limit values for both large consumers and power plants that must be met with regard to the harmonics. In Europe, these limits are defined in the EN 61000-3-2 standard. Let's have a look at the harmonic components of a square wave in comparison. It can be clearly seen that a square wave inverter generates harmonic currents that are much too high to be allowed to be connected to the power grid. However, a square wave is a very extreme example of a distorted sine wave. Today, solar inverters are able to approximate a sine wave much better using pulse width modulation. Yet, even the current waveform of such an inverter does not have a perfect sine wave shape upon closer inspection. This is because in pulse width modulation the square wave is chopped into many pulses with high frequency sampling. This pulsed output signal is smoothed by a filter, giving it a shape as seen here. Low order harmonics are well suppressed in this way. However, it can be clearly seen that the output signal is now overlaid by high frequency harmonics. In order to limit the input of these harmonics into the grid, solar inverters are therefore equipped with additional filters that also reduce the high frequency harmonics. Most inverters meet the requirements of the standard with regard to harmonics and deliver a so-called certificate of conformity for this. However, if the output signal of an inverter has only a low distortion, the THD of an entire system can be higher, since the harmonics supplied by the inverter are combined with the harmonics generated by the loads in the system. In the worst case, resonances can occur here. In larger systems, it is therefore recommended to monitor the harmonics. If the overall harmonic level exceeds the acceptable limit, it may be necessary to use attenuation measures such as an active or passive filter. Let's summarize this teaching unit. To avoid an unbalanced voltage in the three-phase power grid, three-phase inverters must be used from a system size 4.6 kVA upwards. PV systems contribute to frequency control by frequency-dependent active power reduction. Harmonics stress the grids and can lead to the destruction of equipment. In order to maintain the equipment limits for harmonic currents, inverters must use filters. I thank you for your attention.